Good evening, all of you. I am Mukesh, the Dean of the Division of Chemical Sciences, and Professor Rangarajan, the Director of IISc, is not able to come today. And I introduce the speaker on behalf of the Director. And today we have a lecture by Professor N. Ravishankar. He is from the Materials Research Center. He completed his BTech in Metallurgical Engineering from the Institute of Technology, BHU, in 1991. And then he joined our institute in 1993 for his MSc Engineering course. And then subsequently he has completed his PhD under the supervision of Professor Kamanyu Chattopadhyay at the Department of Metallurgy at IISc. So as now it's called Department of Materials Engineering. And after a postdoc stint at Barry Carter's group at the University of Minnesota, he joined the institute sometime in June 2002, just a few months before I joined the institute, and is currently a professor at MRC. And he is very active researcher, very interesting research activities going on in his group. And he specifically worked on fundamental aspects of nucleation and the growth of nanomaterials by wet chemical methods, and the use of advanced electron microscopy techniques to understand structure, defects, and interfaces in nanostructures and microstructure property correlations in functional materials. This is a very prestigious series of lectures in the institute, that's the Institute Colloquium, and I invite Professor Ravishankar to deliver this talk.
Can you hear me? Thank you, Professor Mukesh, for the nice introduction. It's a great honor to be here. It's not often that we get to talk about our work in front of our colleagues. So it's a wonderful opportunity for me to be here. I will talk a little bit about my student days and other things when I do the acknowledgments. I'm going to talk about the science of small things. In preparing for this talk, I just recalled one of the interesting things that I had read. This is from a very nice little monograph called Mathematician's Apology by Hardy. And he says it's one of the first duties of a professor, for example, in any subject, to exaggerate a little bit the importance of his subject and his own importance in it. So that is what I'll try to do. You can pick out which part I'm exaggerating and which part is real, right? It's up to you to do that. So what do we do in our group? We work on really small things, and we make them appear much bigger, literally. So we work on nanomaterials, really small things, and then use electron microscopy as a primary technique to interrogate structure, defects, and properties. So this is broadly the kind of activities that we have in our group. We essentially do wet chemical synthesis to prepare these nanostructures and nanomaterials. Electron microscopy is a primary tool where we look at all the way up to the atomic level. We are interested in different kinds of properties, including catalysis, sensing, and some electrical transport measurements, and so on. And with help of friends like Abhishek and others, we also carry out simulations to better understand the results that we have. So this is broadly the kind of activities. I got a little bit greedy, I should say, in trying to select what I'm going to talk about today. So it is very, very difficult to leave out things. And so I might have overdone things a little bit, but I assure you that I will stop in about 50 or 55 minutes. I hope I'll be able to cover some of the things that I'm interested in. So it turns out that one of the important paradigms in nanoscience or nanomaterials is that, of course, we know that size affects the properties of the material. It is also equally important is the shape of the nanostructure that we talk. If you think of them as building blocks in which we are going to build larger structures, the size as well as the shape of the nanomaterial basically controls the properties in a big, big way. And therefore, shape control synthesis is actually one of the big things. And there's no better way to do shape control synthesis than using wet chemical methods. Wet chemical methods are really, really wonderful and powerful in the sense that you can get exotic, enormous variety of sizes and shapes. But having said that, oftentimes the origin of why a particular shape comes is not very well understood. Okay, and so that is one of the things that we are after. Oftentimes, what happens is that people say that you add this specific reagent and do under these conditions, you end up with this particular shape. But that is not entirely satisfying. So we want to see whether there are any underlying physical mechanisms which we can basically use to understand why specific shapes come about in case of nanostructures. I will talk about two classes of materials. One, what I call as one-dimensional nanomaterials in the form of nanowires, and two-dimensional nanostructures. These are not conventional 2D materials, what we talk today, the TMDCs and so on. These are actually metals and other things which normally don't grow in the 2D form. I will talk about how we can actually attain these things. And of course, a little bit about porous structures and supported catalysts and so on. And finally, some of the recent work that we're talking about. So at the very beginning, I should talk about some symmetry and shape issues to basically set the stage of what we're trying to understand here, right? So I think the story essentially starts a very long time back, sometime in 1611. Johannes Kepler possibly was the first person who really thought about the relationship between what basically material is consisted of and what gives the external morphology. Apparently, the story goes that he was walking in this Charles Bridge in Prague, and essentially he had a snowflake that fell on his coat. And he was wondering about the very beautiful hexagonal symmetry, hexagonal shapes that the snowflake had. Okay, and so of course he said that of course there must be some basic origin, physical origin of why this basically is happening, right? So that was the question that he asked, and so of course he came up with a very different answer, which what we call now as the Kepler conjecture, that possibly material is basically made up of some spherical entities that sort of build up, and so hexagon is sort of a natural shape that's expected to come out when you have close packing. This is the Kepler close packing conjecture that we have. But the interesting thing to realize is that the atomic hypothesis was not even there at this time. So he didn't even know that things were built up of atoms and so on. So he thought that there must be something, these spherical units that basically are built up, and what we possibly call as atoms or atomic entities now that basically build up. So in fact, one of his friends was basically interested in this problem of storing cannons, these cannonballs on the ships, and asked what is the most efficient way to do it. It turned out that this is the close packing that we have, the so-called face-centered cubic, or the hexagonal close packing that we have. The next person, okay, not the next person, the next significant advance, the sort of eureka moment in crystallography basically happened when this is a very difficult name to pronounce, in a French name, right? I think it's pronounced OA or something like that. OA basically, the story again here is that he basically accidentally dropped a calcite crystal, naturally occurring crystal, and he saw that the shape of the broken pieces, the fragments, they sort of resembled what the original piece was. And so he went about breaking crystals. Okay, he went about breaking this in a very meticulous way and found that he called something called as the primitive form of the nucleus or the molecule integrant, however it is pronounced. This is basically the origin of what we call as a unit cell today. So he said that there must be some underlying unit cell of which all matter is built up, and that's what basically reflects. So in spite of the fact that calcite itself might have many different shapes, all those different shapes can be basically built up by considering these very, very small unit cells. Okay, so that was the second thing. That was the another big advance in this field of crystallography, where people try to relate what is happening at the atomic level to what's the macroscopic shape of the crystal. But now, of course, his name occurs prominently in the Eiffel Tower. So as you can see there, I think the first trunk somewhere there is his name prominently appears. So what we now know, of course, is that the symmetry, the point group symmetry of the crystal is what basically controls the shape of the crystals as we know it. And for the same point group crystal, we can have multiple different shapes. For example, in this case, the cube and the octahedral have apparently very, very different shapes, but the point group symmetry for both of these things is ideally the same. If you look at the 4-fold axis, the 3-fold axis, the mirrors, and so on, they're all identical for the cube and the octahedron that we have here, right? So the point is, how does it relate to the crystal that we're talking about, right? When you talk of crystals, the same point group symmetry, for example, can manifest in many, many different shapes. So therefore, what shape forms when we actually try to make a material, either using wet chemical means or any other means? Okay. So among all these possible shapes, we can identify two important classes of shapes, right? The first one, what I call as the equilibrium shape of the crystal. The equilibrium shape of the crystal is the one that has the least energy. Okay. If you sum up all the surfaces have excess energy, if you sum up all the energies of these facets that are there, the equilibrium shape in this particular case for FCC is something like this: the cube octahedral shape comprising of the 1, 0, 0 and the 1, 1 facets. Okay. But in reality, when we actually see the crystal after it has grown fully, we rarely ever see the equilibrium shape. What we actually see is what is called as the growth morphology. That is basically controlled by kinetics. And here we can explain this in a very simple way. Suppose this is the starting shape of the crystal, which is growing. How does the crystal grow? It basically grows by atom attachment to the existing facets, right? Once the growing facet, assume that this facet is growing the fastest. It turns out that finally, after it grows for a significant amount of time, that facet will basically vanish. And what remains basically in the crystal are the slowest growing facets. The slowest growing facets are basically what will be left, and therefore, depending upon what is playing a bigger important role, the thermodynamics or the kinetics, we can get a very wide range of shapes of these nanoparticles, of the particles or whatever we're trying to synthesize, of the crystal in general, right? So let me just start out what do we mean by wet chemical synthesis and how basically this fits into what I'm talking about, right? I will take the simplest possible example of making gold nanoparticles, for example. This is a very, very well-known thing, easiest metal to reduce, and it's not difficult. Typically, any recipe for making nanoparticles, essentially you start off with a metal salt, in this case the gold possibly in +3 oxidation state, and you have to supply electrons for it to reduce. You get monomers of gold, or basically gold in the 0 oxidation state, that basically have to come together to form the crystal. Classical nucleation theory basically tells you, homogeneous nucleation theory tells you that initially there will be few attempts, the crystal forms what are called embryo that are not stable, that basically dissolve, but once it crosses a critical size, you get what is called as the stable nucleus. That stable nucleus is basically set for growth, essentially, right? So the interesting thing is that we have another basically important ingredient in this whole thing, what is called as a capping agent. The capping agent is what basically, if you do not have any capping agent, we just typically keep on reducing the metal, uncontrolled growth will happen, and we get no specific size or shape that forms. So typically we add a third reagent, which is basically called as a capping agent, that goes and sits or sticks itself to the surface of the growing crystal, and that basically gives you the shape. Okay, so that's the overall idea. But the point is this, with a very, very small change. Of course, many times the reducing itself can develop as the capping agent. Okay, so in many cases we have that, the capping agent and reducing are one and the same. Okay, the thing is that, just the example of gold, I showed you just 4 or 5 examples here. With a very, very small change in reaction conditions, okay, we get amazing variety of shapes, all the way from nanorods to plate-shaped structures to wires to pentaglyph twin materials to tetrapods, all kinds of things. Okay, but there's no clear understanding of what will form under what conditions. Okay, it's impossible to understand the whole thing, obviously. But one of the questions was, can we come up with something like this? This is again another important thing. People have been fascinated by snow crystals forever, and this is another important study that basically relates to, this is called the Nakaya diagram, by the way. So basically it relates to the supersaturation and the temperature conditions under which the snow crystals are forming, and tells you under what conditions what shape is going to form. So our question was, can we actually come up with something like this for nanocrystals? Can we come up with reaction or morphology diagrams that will tell you under what conditions basically crystals of different shapes will form? Okay, so that's one of the questions. So what is the fundamental key idea here? I told you about the point group symmetry, and all of these things could have the same point group symmetry. These are very easy to understand, or reasonably easy to understand, just by saying that different facets growing faster or slower, or it's an equilibrium shape and things like that. These are symmetry conserving shapes which nominally have the same point group symmetry as your starting crystal. Okay? But oftentimes what you see are what I call as symmetry breaking shapes. What I mean by symmetry breaking shapes is that out of all the 100 facets that are available here, suddenly one direction, the crystal decides to grow along one direction, or the crystal decides to form one particular platelet form where only one of the 100 basically expresses itself. So what's going on here, right? So clearly there must be some other mechanism by which the crystal decides to actually grow along one direction, or decides to grow in this plate form and so on. So that is the question that we wanted to answer. What are the fundamental symmetry breaking mechanisms? And initially we'll talk about how we can actually form nanowires using this the symmetry breaking mechanism, and later I'll talk about the 2D structures of metals. How can metals form basically in the 2D form, right? I'll start off with the first example of ultrathin gold nanowires. We were basically the first group to basically grow these nanowires without any template. People have grown nanowires by confining the growth within a template, like anodic aluminum oxide and things like that, but usually those are much thicker wires that they get, and usually it's polycrystalline also, maybe not single crystalline always. So I think what Aditi was interested in is basically making gold nanoparticles was very fashionable these days, and she wanted to do some reflexing. I had no clue what that meant. I said, please go ahead and try whatever you want. And so that essentially led to this, formation of these nanowires. Most of the things Okay, so how does the mechanism work? This works by what is called as oriented attachment mechanism. That is the primary way by which basically the symmetry breaking happens in this particular case. It turns out that in this particular case, when we reduce gold to form, we get particles. These particles have the 100 and the 100 facets, as I showed you. This is shown from this high resolution image. But it turns out that the capping agent that I talked about, it actually binds very differently to the hexagonal face and the square face. In particular, it actually binds much weaker to the hexagonal face. Okay, which means that in principle, it may be possible to remove this surfactant or the capping agent so that this one of these things becomes free. So the natural tendency when that happens is particles come together so that the surface can be eliminated. Okay, so that is what is basically happening here. So this dimer formation is basically the first step in the symmetry breaking that happens in the formation of the nanowire. Okay, so essentially when we try to replace the wire, we get something like this. Very, very beautiful long single crystalline wires. Gold, remember, does not want to grow in a single crystalline form, right? And what we have are extremely long single crystalline wires growing along a very specific crystallographic direction. Okay, of course, I have not told you the complete story. Once we have the dimer formation here, basically the third particle that comes in can in principle attach to the other 100 facets that are there, which means that it can still form branch structures. Okay, why should it form a wire basically, right? So that is still a question that remains. So it turns out that this answer comes from something very simple that metallurgists basically call a sintering of particles. So whenever you have two particles and whenever there is a concave and convex region in this particular particle, those are regions of different chemical potential, and mass transport will happen from the region of higher chemical potential to the lower chemical potential, which means that once the dimer forms, it smooths out, and which means that we are left with the two 100 facets at the ends where the third particle can come and attach. So this dimer formation and the smoothing process basically lets you, the growth happen by particle-particle attachment basically, right? So this is the sintering. This is the mechanism. But what about the time scale, right? It turns out that the time scale for the sintering process or this neck growth process I told you is much, much shorter than the time for the average collision between the Brownian particles in the solution phase. So which means that two particles collide, get smoothed. So by the time the third particle comes and collides, it already has only one place where it can basically come and attach. And that is the reason why it basically grows as wire. If you reduce the temperature and do other things, you can induce branching and so on, which we have shown, but I'm not going to talk about that now. Fine. So by the way, this was actually this was I think the first study where we actually showed that ultra-thin gold nanowires can be grown without a template, and it was actually selected as one of the emerging research fronts in a long time back when I still had black hair. Right. So what is the big deal about this ultra-thin gold nanowire set, and why are we bothered about it? Of course, from a growth point of view, this is very interesting. We have been sort of making a living out of this thing, right, for quite some time. So it turns out that this is something that I've said so many times that you think we know everything about gold, FCC metal, noble metal, not particularly reactive, a very simple structure, extremely good electrical conductivity. Almost every single thing we think we know about gold breaks down in this length scale, right? So when we form gold in this particular length scale, less than 2 nanometers in diameter, I should also point out, I didn't point to this explicitly, the diameter of these nanowires is such that it's only like 5-6 atoms thick. These are really, really, really thin wires, okay? Which means that the surface is a significant part of the nanowire that we're talking about, right? We have done a lot of things. I'll just show you 2 examples to tell you how dramatically things change when we go to the nanoscale. Fact, gold has a simple FCC structure, right? So let us see what happens when we go to examine what these wires are. It still has the basic FCC structure, but it turns out that my partner in crime for this particular work, like many other things, was Abhishek's thing. We carried out first principles calculations, DFT calculations. We had a ABC wire, hexagonal cross section. This is the starting state for the wire. If you see the projections, basically these are atomic planes that in projection they look like straight lines. But once we relax the structure, we found something very interesting. The 100 planes, these are the 100 planes in the nanowire. We see atoms actually going above and below the plane, which means that the 100 planes are no longer planar. They've actually sort of undergone some sort of a wrinkling in this particular case. Okay. So of course, this is still first principles calculations. Can we actually see this? Okay. This is where the power of the modern day electron microscope comes in. By the way, this work was done before we had our the Titan, the aberration corrected microscope at AFMM. So some of the initial studies, the microscopy was done in collaboration with other groups, particularly from Belgium and from Germany. But more recently, most of the work that I will be presenting are basically work that is done with our own microscope here, just across the road. Right? So what happens essentially here is that we have these 1-on-1 planes here. After relaxation, this is an exaggerated view. The planes undergo wrinkling. The 1-on-1 planes are no longer planar. They undergo some sort of a wrinkling here. Okay. So how do we look at this particular thing? Typically, when you do electron microscopy, we put it on a grid where you have a very thick carbon support. And therefore, if you have a 2 nanometer wire and a 30 or 40 nanometer thick carbon support, a lot of the signal is basically going to come from the support, and therefore, it may be very difficult to interpret. Therefore, what we did was we actually drop cast the wire or groove the wires on graphene supports. So graphene, of course, is a single layer, very well-defined structure. We can remove the structural details of graphene by using some Fourier filtering and other details. I'm not going to talk about the details. If anybody is interested, I can talk about that later. So essentially, this is the key result. So this is the experimental image that we have. This is a calculated image from basically the simulations that Abhishek was able to show, that we are actually seeing displacements of atoms of the order of the tens of picometers. And exactly like as was shown in the calculations, we are experimentally able to see. This is not an artifact. We have done lots of different kinds of imaging on the larger gold particles and things like that, where we see no such displacement. Okay, so this clearly is a real effect that we see in these ultrathin nanowires as a result of displacement of atoms. Okay, again, as an interesting thing, I'm not going to expand on this further. The same dimension of nanowire, but if we take a different sort of bonding, if we take a 100 nanowire, similar dimension, that does not show any of this wrinkling. So it is not a size effect. It is to do with the fact that the surfaces that are bonding the nanowires are somehow different for this particular nanowire. And essentially, the whole thing was basically there's a very nice surface stress argument to the whole thing, which I'm not talking about, but I'll be happy to discuss later. So this is about the structure. Okay, before I go ahead, since I'll be showing you a lot of what I call your head of stem imaging. This is called high-angle anode dark field imaging in the stem. I just want to quickly tell you what the technique is. Essentially, in the electron microscope, we can do what's called a scanning transmission electron microscope, where we have a very, very fine electron probe of the order of angstrom size that basically scans on the sample surface. And what we are essentially doing is to collect the scattering at large angles. Large angles for electron microscopy is typically of the order of 3 degrees or more, 3 to 4 degrees or more. Okay. So what essentially happens is that we are individually interrogating individual atomic columns that we have. And the scattering is basically related to the number of atoms in the column and or the average atomic number in the column. Thicker the column, more will be the scattering. That column will appear brighter. Also, if you have a higher atomic number, that column is going to appear brighter. So essentially, this is the key idea that we use. This is called high angle because we're collecting at high angles. Annular because we use an annular detector to collect the signal, and dark field because we're not collecting the direct beam, we're collecting the thing. Okay. So what happens when we actually look at one of these particular nanowires? By the way, Paramita did this work. It's very unfortunate. One of my brightest students, she passed away when she was less than 30. Very bright integrated PhD student in the chemical sciences division. And I mean, what can you say? Life is like that. So Paramita basically carried out this work, and this is from a single gold nanowire. And what we are seeing here basically is we can see different columns having different intensities. So what it essentially means, since we just have one element here, it essentially means that the number of atoms in the given column is different, right? So which means that from a single image, it may be possible to find out how many atoms there are in the column. And see, we know that it is nominally an FCC structure, and therefore we can completely reconstruct. From one particular HADF image, you can completely reconstruct the 3-dimensional shape of the crystal. And for example, this tells you that there are 8 atoms here, there are 6 or 7 atoms here, and so on and so forth. And by a priori knowledge, this method was developed by the EMAT group in Belgium, where this work was done. Okay, but it's a very, very powerful technique. Unfortunately, it works only for single component systems, right? When you have even two components, system gets much more complicated, and Sujit is basically trying to figure out how can we do this for 2 component systems. Okay. The second example that I want to give you about gold, excellent conductor, and therefore it's a good metal, and therefore in an excellent electrical conductor. Okay. So the question is, how do you do electrical transport using this on these gold nanowires, right? typical methodologies to actually do lithography and make contacts and things like that. But it turns out that these nanowires are extremely fragile. Any lithography or heating that you do to these things will basically eventually end in breaking of these wires, basically, right? So we had to come up with a method where we basically sort of invert the method, so to say. So what we did, instead of growing the wires and then making the contact pads using lithography, we grow the contact pads and grow the wires directly between the contact pads. Okay, so this way we are eliminating we are doing lithography steps before we are actually making the wires in contact, right? Again, this is done by Paramita, and this was done. Okay, I should also mention Chandni, of course, was a PhD student in Arindam's lab. Of course, she is now faculty in instrumentation. So they were an outstanding team actually, right? So the whole work took about year and a half to complete, and they really worked together to make this possible, right? And so the quick thing, without going into details, this was the paper that resulted as a result of this particular measurements. Resistance versus temperature for a metal. You would think that the resistance basically is supposed to increase. That is the first simple thing that you think of, right? And when we do the resistance, the first thing that we see is that it's actually showing the reverse behavior. That is, the resistance actually is decreasing as a function of temperature. It also shows an interesting power law behavior as a function of when we do the measurements at different temperatures. Chandni basically carried out these measurements. We see that all the curves, all the measurements that we do, the IV basically normalized to various things, basically fall on a single curve. Okay, this is the signature of what is called as the Tomonaga-Oettinger liquid state that we have. It's no longer the simple Fermi liquid description for a metal that we were supposed to have, right? So it's a completely different new state of quantum state of that we are seeing in this really thin nanowire. Interestingly, just a couple of months later, after our paper was published, there was this paper in Nature Physics where they actually deposited gold on germanium substrates. These are single atomic chains of germanium on gold and germanium, something like that, and they saw a very similar behavior. Okay, so but the thing is that the gold nanowire that we have is far more robust in the sense that we can actually move it around. It's stable in the solution phase, and we can do various different things with it. Of course, the other interesting thing was that, again, this is done by the same team, Chandni and Paramita. What they did was they actually varied the distance of the gold wire from the substrate. Of course, when you do a measurement, we have to have the wires on a substrate where you do the contact pads and so on. What they did was they actually vary. For example, they can have how I'm not going to talk about how this is done. You can have two bilayers of this olalamine. So which means that it's at a sufficiently large distance from the substrate. We can have one bilayer, or we can just clean off everything and have it directly on the substrate. We see that the substrate has a dramatic effect on the nanowire, in the sense that in this particular case, in this case where this is directly on the substrate, what we see is a so-called variable range hopping behavior for transport to the nanowire. This is the classical behavior for any disordered system that we have. And the original behavior of the TLL, the transport, completely changes. The IFMM results clearly show that we have a nice distribution 2 nanometers, 4 nanometers, and 6 nanometers away from the substrate, and these actually show different behavior. So why is this interesting? It basically tells us that it is possible to modulate the transport through the nanowire by external means, okay? And that is basically the basis for any sensing that we can have, right? So one of the classic papers in this particular field, I'm sure many of you have seen this, is from this paper where, extremely highly cited paper by Charles Lieber, where they basically showed that silicon nanowires can be basically used as sensors. Analyte basically, adsorbing on the nanowire can cause electron doping or electron removal, whatever it may be, and therefore cause change in transport or the resistance through the nanowires, right? Metal nanowires, you do not expect this to happen. To put it very simply, metals have tons of electrons, right? And therefore, addition of a little bit of electron or removal of a small amount of electrons is not going to change anything much. So you do not expect a metal nanowire to exhibit this behavior, okay? The other thing is that the other scattering mechanism or other things more or less remain same, and therefore, we normally do not expect it. But in these length scales, whenever we have nanowires of these dimensions, what essentially happens is that the surface is basically the dominant thing in these nanowires, and it is possible to basically modulate. What Abhishek also showed that there is a significant reduction in the density of states at the Fermi level, and therefore it doesn't have as many electrons as like in a bulk metal, right? So this was again we showed that it is possible to have semiconductor-like sensitivity in these nanowires. These are just first principles calculations, and we actually showed using the calculations that it is possible to have sensitivity higher than what is demonstrated for a silicon nanowire. Okay, and it turns out that the electron affinity, which is what you expect, right? How much electrons they say that donating or giving, that's actually related to how much resistance or conductance chain that you're having. So it scales quite nicely with electron affinity in this particular case. Okay, of course, in collaboration with Avik's group in the physics department, we were able to actually do the measurements also. We were able to show that gold nanowires without any additional thing is able to sense, for example, methanol in this case. And when you introduce methanol, it actually absorbs. You see a huge change in resistance. And when you remove it, of course, it drops down and so on. So this actually is a very, very interesting sort of sensor that's not expected from a metallic material. Okay, so that's a very interesting thing, I think. So again, we have a situation where gold behaves completely differently from what we normally expect, right? And of course, I'm not going to talk about this. We also showed some other studies where we are able to grow these nanowires, gold nanowires, on zinc oxide, for example. And it shows enormous improvement in photoelectro-oxidation of ethanol, things like ethanol, right? If you shine light, electron-hole pairs are created in zinc oxide that gets transferred to the gold, and therefore it shows huge increase in the photoelectro-oxidation for ethanol. Okay. Again, tellurium again shows some interesting thing, ultrathin tellurium nanowires. Okay, fine. So more recently, so I hope I've been able to convince you that gold nanowires, when you make things in this really thin form, it really shows some interesting new thing. I just showed you only 2 examples. There are many, many other things that we have talked about. One of the questions that we got asked is that, okay, so what, you're able to make gold. Can you make any other metal, or can you do any other thing, right? So it turns out that for a very long time we could not. It turns out that the very, very fine balance between adsorption and desorption and things like that in gold, that is the only system that basically worked. More recently, we've been able to do things like platinum nanowires and, interestingly, alloy nanowires. We start off with the gold nanowires itself and then add a second element, and we can actually make alloy nanowires. Okay, this is also very interesting. Dipanita actually did this. Gold nanowires in the solution phase are unstable, and therefore directly we cannot do any alloying. So we have to keep it in a non-polar solvent where the gold wires are stable, and add the second metal through a non-polar polar solvent where it's basically soluble, and have the reaction happen at the liquid-liquid interface, basically, right? So this is something that we were able to do. And I just show one particular interesting example here. In this case, we have a gold palladium nanowire, and what I'm showing here is a high-angle angular dark field image. Okay, and what you're going to see is atomic number contrast. As prepared wire shows something like this. So these are all the atoms of gold or palladium. We don't know, but once you heat this wire in a carbon monoxide atmosphere, it turns the carbon monoxide or palladium has a strong affinity for carbon monoxide, and you get what's called surface segregation. Palladium from inside the nanowire basically comes out, and what you can see here is a brighter core, which basically corresponds to higher atomic number gold, and a less brighter shell, which corresponds to palladium that has basically come out. Okay, and we can drive this back and forth. If we heat this back in inert conditions, it basically mixes back. But if heat it in a carbon monoxide environment, basically you're able to drive the palladium outside. And this is interesting because palladium in this case is the active metal, and therefore we can actually tune the catalytic activity, right? For gold, palladium is a very interesting system that people have been working on. We can actually drive the active metal, palladium. So in principle, we can have a very, very small amount of palladium, right? And get what are like single atom catalysts that are dispersed on the gold nanowire, for example, right? So this is an interesting thing, but clearly TM actually helps us to show that there's a clear segregation, that we can do back and forth in these nanowires. Okay, so far I talked about one-dimensional nanostructures. I'm keeping a watch on time. So I'll talk about the 2D nanostructures now. 2D nanostructures of metals here, right? And here is where I will try to show you that we can come up with something called like morphology diagrams, where you can predict under what conditions different shapes will form, right? So again, there are literally hundreds of thousands of papers and hundreds of mechanisms that are proposed. These are very, very famous papers, by the way. All of you know about the biological method, light-induced method, gold nanoprisms, and all kinds of Merkin's paper and paper from anyway, all of these papers. Most of you working on chemical synthesis know most of the papers that I'm talking about, right? But many, many different mechanisms. Okay, the typical again, I'm not going to talk of I'm not trying to dismiss each of the mechanism, but again, the explanation is quite unsatisfactory in the sense that the role of surfactant cannot explain the formation of 2D structures, because there are several equivalent phases, as I told you, and therefore there must be something far more fundamental that's happening here, which can basically explain this, right? And so what is that fundamental thing? Okay, it turns out that crystal growth under different supersaturations or driving forces happens under very different, in very different ways. In particular, when you have very low supersaturation, basically it grows by what's called a spiral growth mechanism. By the way, this is one of the first demonstrations that there are things called dislocations in materials, that crystals are actually growing under very low supersaturations where you don't expect them to grow. And people realize that it's because there are these screw dislocations that are present and so on, right? In the intermediate regime, where the driving force is low, it basically grows in a layer by layer fashion, which means that the complete layer gets filled up before the third layer or the next layer starts. And of course, when it's high driving force, there's no, atoms can pretty much come and park anywhere, and you get three-dimensional growth. Okay. If you think about it, this layer by layer growth automatically gives you a physical mechanism by which you can get two-dimensional structures, because the layer has to complete fully before the second layer comes. Therefore, the thickening rate will be much smaller than the lateral growth rate, right? So this is the key idea here. So John Kahn, right, one of the our gurus in physical metallurgy, basically came up with this thing. Of course, this is very well-known thin film literature also. He came up with what driving forces are required for solidification in particular, where things can grow in a layer by layer fashion and things can grow in a continuous fashion. So it turns out that this is the driving force. Basically, it has only two parameters: the interfacial energy, where the crystal is growing, and the step height, the monatomic step height in this particular case. So he identified a range, the driving force below which only 2D growth will take place, and above which 2D growth, three-dimensional growth will take place. So the question was that, is this actually responsible for the formation of 2D structures in most of literature, and can we sort of reproduce it? The really interesting thing is that we wanted to eliminate the role of surfactants, right? Because otherwise people will blame it on the surfactant. That's what is basically causing the thing. It turns out that gold can be reduced, gold salt can be reduced just by water. We don't need any reducing agent or any capping agent. Okay? And these are simple redox reactions. In high school chemistry, we can write down what is the E for the particular reaction, and delta G is minus NFE. We can write down expressions for delta G. The very beautiful thing about chemical reactions is that we can drive the reaction forwards, backwards by changing the value of delta G, by changing the reaction conditions basically, right? So, so when we combine this, we see that we are left with parameters like temperature, pH, and concentration of gold salt and so on. We came up with these kinds of diagrams where we have pH and temperature, and this gray regime basically tells you that water cannot reduce gold salt. Delta G is greater than 0. The yellow regime basically tells you that it is a low driving force regime. This is the intermediate transition zone, and this is the high driving force regime. So basically, we expect to see 2D shapes in this particular case where it's growing in a layer by layer fashion, right? And of course, for silver, it's much less noble. It's much more difficult to reduce it using swan. Therefore, the gray zone is much higher. And what we have, results, experimental results, when things grow under low driving forces in the yellow regime that we talked about, we indeed get plate-shaped structures, right? So all of these things are all grown. And when you increase the driving force, for example, it actually forms this more equiaxial three-dimensional growth, right? So it basically tells you that the driving force for crystal growth basically plays an important role in controlling the morphology of the crystal, right? So this I think was a very interesting result. Okay, so more recently, I think we've been able to show this experimentally using the electron beam. This is done in the Ernst Roscoe Center in Jülich, where basically we're using the electron beam to reduce gold, right? And here, this is the high driving force regime, where you see lots of nucleation and gold particles that are forming. We're directly seeing things forming inside a liquid in the electron microscope. Whereas in the low driving force regime, when we have small number of electrons that are impinging, right, we clearly see the formation of 2D crystals. So this is still work in progress. We're still trying to quantify things. Okay, but it's quite interesting that we can directly see this different regimes that we have here, right? So, and a very interesting aside that came up. I still remember with Vishwanath we were having this discussion. He was also working on things like hydroxyapatite, right? And so it turns out that hydroxyapatite is a wonderful nanocomposite. If you think about it, it is comprised of two things: collagen, like a squishy thing, and hydroxyapatite is a very brittle thing. Right? Both of them cannot, they cannot carry loads basically. But if you combine them in this particular form, That is the reason why I'm able to stand, even though it's a little bit of pain and so on. But the point is that it becomes load bearing. So this is a natural nanocomposite that we have, and that's because of the way nature has produced it, right? And of course, there is a connection to the institute about the structure of collagen. Students, I hope you know who this is, right? So, okay, it turns out that the hydroxyapatite in the bone is basically in the form of platelets. And existing theories basically told that since it's basically forming within the collagen matrix, it's confined to form in the form of platelets. Okay, so that was the general explanation. Okay, this hydroxyapatite formation is a precipitation reaction. It's a mineralization reaction, right? We have a soup of phosphates and calcium and hydroxyl, whatever it is, and basically hydroxyapatite basically precipitates during the initial formation of the bone. And therefore, we can write down delta G for this particular reaction, where it's given by the ionic activity product, by the solubility product. And we ask the question, can we actually predict under bone biomineralization conditions whether it's expected to form platelets, right? And indeed, we show that we can actually come up with morphology diagrams for this particular case and showed that under body biomineralization conditions, which is neutral pH and 37 degrees centigrade or whatever, it actually indeed forms platelets with exactly the same orientation as in the human bone. Okay, so these are some important implications that this fundamental thing about crystal growth and low driving forces has important implications here. I think I should speed up or I should cut down on a few things. Okay, so maybe I will just skip this then. I just wanted to show this because my brother has always been asking me to try this notebook LM. That it prepares very nice things and so on. So I got curious and wanted to give one of my papers and asked you to create the slide for me. And this is what it did for me. Okay, so I'll just leave it at that. Okay, you can decide whether it's good enough or anyway. So we are able to produce the other high end of very high driving forces and so on. I will skip this in the interest of time. Okay, so there's a very interesting transformation that happens whenever we heat a highly porous material. We expect that it basically sinters quite readily because it wants to reduce the surface area, but it turns out that always it basically forms hollow structures. And we try to understand this. Abhi is here. We did collaborations to do phase field modeling, and we actually, I'll just leave it at that. If anybody is interested, I can talk about this later. Okay. Okay. So now I want to talk about another simple example where very, very simple idea basically can give us something quite interesting. Okay. All of us use microwave almost on an everyday basis. We heat it. We heat our tea or whatever it may be, and we see that the cup does not get heated, whereas the liquid inside gets heated. Typically, which contains milk gets heated, right? So typically, when we want to make supported catalysts where we have metal nanoparticles in the substrate, what is done is the simplest method, common method is what's called the co-precipitation method, right? We mix up the support and the metal salt and heat them together and sort of hope and pray that the particles form where we want them to form. Okay, of course, I'm slightly exaggerating things here. But the point is, can we do it in a more systematic way? And that is where the idea of the microwave comes in, right? Microwave is basically, if you think about inside-out heating, and therefore, if we have supports that is within the solvent, we can selectively heat the support and cause nucleation of particles on the support. The window that we have is very, very small. Of course, we did the initial experiments using a simple 4,000 or 5,000 rupee LG microwave. Later, we went and got a commercial microwave system for doing synthesis, but we were able to actually show that it is possible to control specific heterogeneous nucleation on the support and no homogeneous nucleation inside the solution phase. This is what we basically want, and it is possible to control that. Okay, so what does microwave heating depend upon? It depends upon the dielectric loss of the material that we talked about, right? Silica has a very low dielectric loss, and that's why the cup doesn't get heated when we try to. Water has a high dielectric constant. High dielectric loss and also a dielectric constant. Therefore, our food gets heated much faster, right? So that's what happens in a microwave. When we see that when we take things like cerium dioxide and titanium dioxide, we see formation of very, very uniform particles on the support. Whereas when you take silica, it doesn't really form because the silica doesn't get heated as much. And what you're basically seeing are like particles that are formed outside and that have dried when you've done the drop casting. Okay, so basically using a very simple idea of microwave. Now we've been using this quite extensively to make this kind of supported particles for many different applications. Okay, the last, again, this is a very nice example of extremely fine particles of gold that we formed on zinc oxide. Okay, in the last maybe 5-10 minutes or so, because indulge me, I need some about 5 to 10 minutes to do my acknowledgments. I'm not going to get the opportunity otherwise, so in front of all of you. So I'm going to run through some of the newer work that I'm talking about on layered materials basically, right? So more recently we've been working on layered materials. This has been likened to what we do with the Lego, for example, right? Lego, you have all these pieces and you can stack them. The Lego piece itself is very strong, which means that the in-plane bonding is very strong, but you can very easily remove the individual pieces. There are weak van der Waals interactions between the Lego pieces. Exactly similar these materials also are, right? That is, there is strong bonding in plane, very, very weak bonding, right? There's a lot of very, very nice work happening in the institute on 2D materials, where the people are interested in exfoliation, making twisted bilayers and so on. I'm not going to talk about that. We are interested in the Lego in this particular form, putting two different layered materials together. Okay. Simple way to do is to what I call vertical heterostructures, where I can take different Lego pieces and stack them on top of other. Okay, this is reasonably easy to do. Okay, because these just van der Waals interactions, we can actually do that, exfoliate them, restack them, and so on. But if you want to put two Lego pieces side by side to form lateral heterostructures, you can see where the problem comes, right? I've exaggerated it, and therefore it looks blurred. The Lego pieces themselves may not be of the same height. I'm just showing an analogy here, right? And therefore they'll not fit in very nicely when you try to put them together, right? Or you have to sort of strain them to be able to put them together, right? So in layered materials, particularly when we want to form lateral heterostructures, we get this interesting kind of strains that happens, right? But why is this particularly interesting, right? So when we want to put these things, the block size itself could be different, and the spacing between the blocks itself also could be different. Therefore, when you try to put this is a theory paper done by Boris Jakobson. So where they actually try to put graphene in single layer boron nitride. This is only one layer, and it turns out that the boron nitride is under compressive stress, right? When a thin sheet is under compressive stress, basically what happens? Imagine pushing through a paper, right? It basically is going to bend. It's going to form a ripple like this, right? That's exactly what happens when you try to put graphene and boron nitride together. Because of the compressive stresses, these are actually going to have ripples that forms. The same kind of thing will happen even within the bulk of the material. Okay, when you put two layered materials together, because of the strains that come within, you basically form ripples, and you get these defects called replications, the equivalents of dislocations in these layered materials, because the out-of-plane bonding is very, very weak in these kinds of materials. Therefore, we get relaxations that are not possible in bulk 3D materials. Okay, so that is the interesting thing from a fundamental point of view in these kinds of materials. Fine, so I'll just show you two examples very quickly. So how do we make these layered materials? There are two ways broadly. Again, simplifying, we start off, by the way, these layered materials naturally grow in the form of platelets. Okay, we don't have to do anything special to form in the because of the highly anisotropic bonding. That's how they form. One way to do is basically we can replace either the M or the X to form these kinds of structures. We can replace X with Y to get My, or we can replace M with N to get NX. This is one way to get lateral heterostructure. The other way to do is to basically we can start off with the MX and then grow NX on top. Again, it will actually turns out that it will only grow in this particular fashion because you already have a template from which it can basically grow, right? These are the first one is basically called as an ion exchange reaction. We are either replacing the anion in the material or the cation in the material to form these lateral structures, right? So very quick insights on what we have obtained. All of this is possible, by the way, only because of the modern day electron microscope. Okay, none of this would have been possible without the the resolution that we are looking at basically, right? This is an example of tin sulfide and tin selenide. Right? This is normal. We are basically replacing tin sulfide with tin selenide. It also turns out that the sulfur actually diffuses out much faster than selenium coming in. Therefore, you get what are called Kirkendall voids. Right? This is very well known in diffusion literature. So this is what we call okay. The most important thing is that looking at it in plan view from the top is not really going to tell you what's happening, right? Because all the action is happening in the cross section. Therefore, we really need to cut the material and look at what's happening in the cross section, right? That is where the use of focused ion beam is very helpful, that we can actually section the material and look at what's going on in the other dimension, the Z dimension, if you will, right? So the interesting thing here is that we have tin sulfide here, on this side tin selenide. We are seeing some sort of cracks that are forming in the tin selenide. The lattice parameter of tin sulfide is 5.89, which means that it's closer, and tin selenide is larger, which means that this region is under tensile stress. Okay, and this of course shows you there are cracks. If you go to a high resolution image, what we'll basically see is that we have these very, very nice extra half planes, extra dislocations that are coming at the interface. And the tensile part is basically, because these are weakly bonded, it basically drives crack within these materials. Okay, so this is only possible by looking at things in cross section, right, as to what is happening at the interface here. Okay, this is exactly what is basically shown here. The other interesting thing is that ion exchange reactions are very site selective. What do I mean by that? When I have SN and SC, SN and sulfur, there's only one type of sulfur site, which means that both sulfur sites are equivalent. There's no problem at all. Whereas when I have something like bismuth telluride, right, it's a 5-layered structure. 5-layered structure where we have tellurium, bismuth, tellurium, bismuth, tellurium. This is a cross-sectional image clearly showing very beautiful this quintuple structure as it is called, right? Dorothy basically tried to exchange tellurium with selenium in this particular case, and what she found was that normally, right, if I told you that it's selective and only one side, these two are non-equivalent, right? Because remember, this is free. This only has a van der Waals part, whereas this is actually bounded on both sides. Normally, if you think that only one of them has to exchange, your bet would be on that the outer layer is actually going to be exchanged much more easily. But what she found was completely different. Selenium is basically replacing the central layer. If you take a Haldef image, selenium being lower atomic number than tellurium, we can see that, you can very clearly see in this image that the central layer is basically what has uniform tellurium, tellurium, tellurium has now become tellurium, selenium, tellurium. Okay, so it's a site selective exchange that's happening here, and we can directly see this only because we're able to do cross section and look at it, look at this at this resolution, right? The third example that I want to give is basically the lateral growth, where we start off with bismuth telluride and then grow antimony telluride. It turns out that there's a very large difference in time between growth for these two things, and therefore we're able to grow bismuth telluride first, and then the antimony telluride grows on top, right? So this is what it looks like. You have bismuth telluride inside and antimony telluride outside. Okay. If you look at the simple bright field image, okay, I want to tell you that it's not always about atomic resolution. Even a simple, very innocuous looking bright field micrograph can give you so much detail. What we're seeing here are what are basically called as bend contours. Any real material inside the microscope is getting bent, and therefore we have these bend contours. The really surprising thing is that the bend contours here are absolutely parallel to each other, which basically tells you that the bending that we have in this case is very uniform. Okay, and more interestingly, when you tilt, for example, the bend contours will move, and the intersection of bend contours basically tells you different zone axis. Okay, so we can say that this part of the crystal has a 0, 0, 0 in orientation. This part of the crystal has a 2, 4, 2, 9 orientation, and so on. We can actually map out the crystallographic orientation of every single part of the crystal from a single image, and of course taking the diffraction patterns here, right? And we can estimate what the average bending is, and therefore radius of curvature, all from one image, and of course the corresponding diffraction patterns, right? So therefore, it turns out that in this particular case, using molecular dynamics simulations in collaboration with Guru, we actually showed that these actually undergo this kind of a bending. What starts off as a flat thing becomes sort of like a bowl because of the different kinds of relaxation that happen in these materials. Fine. Okay. So the very last example, I'll only take 2 minutes. This is transformation in lead oxide. Lead oxide is another very interesting layered material, and it exists in two forms: the tetragonal form and the orthorhombic form. Okay. It turns out that the tetragonal, okay, here the orthorhombic form, slightly different arrangement, and the spacing, the van der Waals spacing is larger. The tetragonal form, the van der Waals spacing is actually much closer to each other. Okay, and it turns out when we grow these crystals, it actually always forms the orthorhombic layer on top. But what I want to show is here is this: inside the tetragonal region, we get dislocations, and the strain in the regions close to the dislocations, right? Whenever we have strain close to the dislocation, again I showed you the crack opening in the other case, right? In this case, the crack opening that happens inside the material basically leads to transformation. That is, we get locally the higher, the orthorhombic form basically coming up, becoming stabilized in regions close to dislocations. Okay, so this is a very, very interesting observation that a local strain can basically induce this kind of a polymorphic transformation. More interestingly, we wanted to ask a question: can we induce a reverse transformation? Namely, can we actually compress the orthorhombic phase and transform it to the tetragonal phase? Okay. Again, this calculation was done where it actually showed that it is possible to go for a transformation from the orthorhombic, from the tetragonal to the orthorhombic as a function of the van der Waals distance. We did indentation. on the orthonomic phase. Okay, and clearly we see that something dramatically different has happened here, right? Which means that we are able to compress the layers and transform it to a new phase. This is still not quite the tetragonal phase. It's still slightly different to the tetragonal phase. It is sort of a metastable precursor to the tetragonal phase that we have here, right? Using IDPC, we can reveal where the oxygens and the lead positions are. And if we use this as a starting point and again do the calculations, it turns out that this thing will, after relaxation, it basically goes to the tetragonal phase. So clearly tells you that it is a metastable variant that we're seeing as a result of the indentation that eventually will go to the orthonomic phase. So I think I will. That concludes the technical part of my thing. I wanted to talk about many more things, but in the interest of time, I will stop here. But please hear me out for the next few minutes, because this is the opportunity for me to do many in the front of the institute community. I was a student here, as you know, right? Before I go, I want to first of all thank my group members. All the work, all the beautiful microscopy, everything that you saw was done by these people. I'm just here standing as a representative talking about the work, right? So they say that, right, the students do the work and the professor makes the PowerPoint. In some cases, I did not even make the PowerPoint. They made the PowerPoint for me, right? So I think, all credit to them. A really wonderful group of students. I've been really fortunate. And I think I'm very proud and happy that all of them are doing quite well. Okay, this is where they are. I hope I've not missed out. It turned out that in one of the previous talks, actually, I've forgotten one of my current students. And he was quite upset about it, right? And he came and told me, did I do anything wrong? Why did you remove my name? So I said, OK, old age, nothing else, right? So this is what it is. Like, so this is my students. And again, I cannot emphasize how proud I am of all of them. Equally important, collaborators. I've been really fortunate to have really wonderful collaborators from all over and very good friends and collaborators. Again, I'm not going to read out the names, but only one thing I'll point out. This is written in alphabetical order. Top of the alphabetical order is Abhishek Kumar Singh. He is number 1, actually. He has been my strongest collaborator and go-to for most of the things that we've been talking about. Again, this is not in order of any importance, but I can tell you all of them have been contributing quite significantly to our work, and I'm really thankful to all of them. Okay, sometimes we have my former students who are now faculty. I'm collaborating with them, so that's actually quite nice, right? Okay, so now I have this is the difficult part, right? I am a proud alum from the metallurgy department in BHU, and I think by a rather strange sort of coincidence, 2 of my classmates are here. Right, so that's Manohar and Bhupal. I'm here for you. So they happen to come here, and I should tell that Manohar was the last button roll number. I was the last roll number, so we always ended up doing labs together. Right, so we had the distinct luck of being grouped together always. Anyway, so it was wonderful times in BHU. I want to make particular mention of one specific Professor Lele, as many of you might know. Gentleman scientist. I'll just leave it at that. There's so much to learn from him. His voice never goes above a whisper. You have to strain yourself to hear what he's saying. He did not follow G.H. Hardy's things, that he did not go about saying that or exaggerate about things he had done. Okay, absolute role model and really important things to completely. I'm grateful that even when we were undergrad students, he used to sit and read line by line and explain things to us for our undergrad project. We were lowly undergrads, remember, right? So he still did that. Wonderful teachers in BHU, metallurgy department. This was at a time when metallurgy was still considered important, right? So unfortunately, it's geopolitical things. All of the things had to come back to realize that things like metallurgy and mineral processing are important. Unfortunate, but anyway, that's how it is these days. But so this is. I think metallurgy, of course, is still very important. No questions about that. IISc, right? I have 1 more hour, so I came here as a naive undergrad student after finishing in BHU, thinking that science was all about pursuit of truth and great things and things like that. Soon brought to ground, right? Of course, it's important. After all these years, I still remain a naive professor. Okay, so I should remain that. Many of the things that I believed in, I still believe in, and I think rest is basically mostly noise. Okay, so the important things still remain. Professor Casey is here. I'm extremely glad. Somehow he misses all my talks, right? I told him that you have to be here for today's talk. Okay, it's a very, very fortunate and proud moment for me that he is here. I was not his best student. Okay, in fact, if you look at the number of papers that I published when I was with him and so on, nothing very great. But he was extremely, and everybody in the group got shouted at. I was one of the few exceptions. He never shouted at me. I don't know why. I think he liked me very much, right? And but the important thing is that I tell my students that I can teach you microscopy, I can teach you material science, but I cannot teach you to be excited about science. Okay, that's something that has to come within. But I learned that from Casey. Okay, how to be excited. He was naturally excited about things, science and things, and so I think that is the best thing that I learned from him. Thank you so very much, for being there throughout, right from the student days. Professor Ranganathan and the Sigma Tau group, I should make special mention. I was debating what to do in my final year, and Professor Ranganathan had come out to BHU to give a talk. This is something called on golden solids. I don't know if my friends here remember. And I was completely floored, right? I thought IISc is where I want to go. I had no other plans. I drop everything else. Let me go to IISc. That was what I wanted, right? So his talk and the way he spoke, carried so much excitement and things for me. The Sigma Tau group, which is basically where Professor Ranganathan, Professor Casey, Abhi, Vikram, and so on. The Saturday seminars, were something of an event. I should tell you that I came to the institute, just for time scales, right? Just for the students in particular, a very, very long time back. Okay, Nesara used to be called MS, right? And coffee in the coffee board was 85 paisa, right? For students, 100 paisa is 1 rupee, right? So this is how long back I basically joined the institute, right? And so absolutely wonderful. I cannot say. What do you say about the institute, right? Wonderful teachers. Professor Ranganathan had this course by Professor Vittal Rao in linear algebra. Professor, I never let this thing they say, right? Never let RTP interfere with education, right? So I attended classes all over the place, different departments and so on. And Professor Mukunda from physics department, classical mechanics, linear algebra in the math department and so on. Absolutely wonderful teachers. Huge influence on me. Okay, I try to, I want to be a good teacher. I don't know if I am, but I try my best. Okay, there is a saying in Tamil that Kana Mailada Kandrindavan, which means that looking at peacock dancing, the turkey also wants to do the same sort of thing, something along those lines, right? So I try to copy them, right? And so, but only my students have to tell me whether I'm successful. But having said that, I should tell you that I'm extremely proud that wherever I go these days to any institute in India, there's always somebody who comes and tells me that I did your course, right? It's almost without fail. My first reaction is that please don't hold that against me, right? So, but anyway, I'm extremely proud of that. So many of them or most of them are doing very, very well. I'm thankful. I learned more from them actually than the other way around. And lastly, but not the least, my postdoc mentor, Barry Carter. Anybody in microscopy knows, his name and what he has done. Authoritative textbook, absolutely wonderful mentor. And my go-to, any advice, anything that I want, after Casey, it's Barry that I go to, right? And so he has been completely supportive. And this young man here, I hope you recognize this young man. I only could find one photograph. This young man here, of course, is Professor Casey, and I think you can figure out where I am in this particular. I could not find any more suitable photographs. Okay. I am particularly happy. Okay, before I go to AFMM, I should also mention that I'm particularly happy that, in election time in Tamil Nadu, maybe in other places also, suppose if the crowd is less, what they do typically, they bring cartloads of people. They pay them and bring cartloads of people. I've also done that, right? My family members are here. My classmates from BHU are here. I conned them into coming here, right? And so, and my, my brother is here. So I think I should also tell, my mother actually last attended my thesis defense in my PhD thesis defense, okay? And I hope she has found some improvement in, right? there's a very specific reason I'm telling you this, right? In school, there used to be elocution competitions, and then, she writes beautifully in Tamil poetry and everything. So she used to write. I had the higher than average capacity to memorize things, right? And so she used to write very nicely, and then I always got the prize, not because I spoke well, because the writing was so good, right? And she always used to say that. She always used to say, this, I always still remember to this day. This is very long back, right? She always, two things you have to remember. When you're preparing, you prepare as if, you don't know anything. The audience actually knows everything. When you go and deliver, you always talk as if you are the boss, you know everything, the audience doesn't know anything, right? So this is something that has actually stayed with me all these years, right? So thank you. I think that advice still holds good. I came here, again, just a couple of more minutes. I came here with a very, very, ambitious proposal on metal ceramic interfaces, right? We had a 25-year-old vintage microscope and a 15-year-old microscope that is, again, very close to age and so on. That was very ambitious. But having said that, very soon, this is the turning point in my life, I should say. Almost within 2 years, 3 years within my joining the institute, this thing happened. And the primary people responsible, what started off as the Institute Nanoscience Initiative, primary people responsible here are Professor Casey and Professor Dipankar Banerjee. Big thanks to them for enabling all of whatever was possible, setting up the center. Both have been my mentors over the years, as different people as you can think of. Casey is instinctive and on the spot, and it's very difficult. It's very difficult to follow him. The other extreme, other end of the spectrum, Professor Banerjee is completely methodical, right? You can just follow. You can write down a script and then you exactly follow the way he does things. But anyway, I've learned both from a lot of them. Thank you very much for that. And we continue to do small things, as I told you, in the hope that something big comes one of these days. Thank you very much for your attention. Sure.
So we have some time for discussion.
Yes.
First question was, you mentioned in the beginning that the capping agent is labile when it is bound to the hexagonal phase.
Yes.
What is the reason for that?
Okay, so there was this earlier paper where they were investigating the how methylamine, for example, as a model system, how they wanted to study basically how single DNA binds to gold surfaces, and they're doing it on this cuboidal shape. And what they found is that they used methylamine as a model system for that. And what they found that there's a significant difference in the binding energy. Of course, a hand waving approach would be the packing, the close packed plane versus the other plane, and so on. They found that actually the surface energy of the 111 plane is much smaller than the 100 plane. And from their calculations, they found that the binding is significantly different on the 111 as compared to the 100 plane. So that was our starting point. Of course, none of this happened by design. It happened, and therefore we went back and tried to explain what was happening basically.
Okay. Another question, Mukesh. In the gold palladium experiment, where the carbon monoxide comes and binds on the palladium surface, does it happen in the solid state or does it happen in the colloid? The phase segregation of gold and palladium.
This happened. We take the wire and then heat them in a carbon monoxide, not in the solution phase.
What temperature?
In principle, we could possibly do it in the solution phase also by dissolving carbon or maybe. But what we did was to take it heat it in a
furnace.
Yeah.
What temperature?
Temperature, if I remember, it was something like 120, 150 degrees or so.
Okay, not too high.
Not too high. This will break. If you go very high, this will break.
Okay.
I think it was around 150, if I remember correctly.
All right. Yeah. Thanks.
Yes, Satish.
Just wondering, you mentioned about the catalytic activity of the palladium enhances when you grow these alloy nanostructures. So what is the physical mechanism? Is there any change in Fermi level, surface area?
No. What I meant was that I didn't actually say that it enhances. Between gold and palladium is basically the active metal.
Okay.
And if you have a mixed state, most of the palladium is sitting within the bulk. So what we are essentially doing is to drive it to the surface. We have not done exact calculation to see how the d bands and things change and so on.
Okay.
But there could be changes. But we are actually maximizing the use of the active metal by driving it to the surface.
Okay.
Right. So there will be electronic effects which we have not investigated.
Okay. That's fine.
This is more from an industrial and commercialization aspect. How many patents has the nanomaterials group resulted in?
Okay. I will refer you back to G.H. Hardy if you have read the book anyway, so it doesn't matter. So at the point is that we have been content, shall I say, in doing fun things in the lab and then leaving it at that. Maybe a good thing, maybe a bad thing. Some of the things, of course, we have actually 2 or 3 patents. That's a different matter. But for most things, actually, we have been more or less sort of content to say that, oh, this has been fun, and understanding this has been good. Hopefully, somebody can use it and, do things. In our lab, we're not so big on patenting.
So, Professor, along those same lines, if you wanted a slightly larger quantity of material to process into a working device of some kind, is that where agglomeration becomes a problem?
Agglomeration can still be controlled, but scale up is always an issue for anything, right? We are talking milligram, tens of milligram scale. Okay. Having said that, think, for example, particularly the microwave thing that I talked about. It is possible to have fairly large microwave reactors and scale up, for example, the catalyst production and so on. We are not even attempted that. Some of the things are more amenable to scale up. Some of the things probably not. The gold nanowires will remain in these little devices and things. Maybe if you want to use small sensors and things like that, may be possible. But it's not going to happen in the kilogram quantity, not at all.
Thank you.
Thank you.
Genesis for the word you have coined reflocation.
Replication, yeah. So these are actually.
I never heard that.
This is actually a new term that has come up in the layered materials literature, where actually between 2 layers, actually you have ripples within the layer in between, and these are and they have some characteristic spacings and so on, and so these are what people call as replications. In the, it's a fancy name for, sounds like dislocation, but it's actually a ripple. Yeah, so. Probably not. There's no, probably not. No, much smaller. We have not really measured it, but if you want, okay. Let me tell, from experimental point of view, we heated them up to the gold nanowires up to 120 degrees, and they don't melt. We also carried out in situ experiments inside the microscope, right? Bulk melting point of gold is 1063 or something like that centigrade. This will be 200 or less.
So the kind of what about the defect concentration?
Yeah, so the defects you meant in terms of extended defects or point defects? There will be point defects surely with whatever the equilibrium concentration is, but if you think about it, it will be 1 per whatever very long length of the wire, because the defect concentrations, you can actually count the number of atoms that you have here, right? So in terms of the numbers, it will actually be a very small number. One of the things is that in nanoparticles is that, right? The numbers become so small that you might actually have 1 vacancy or even no vacancies in some case, right? But having said that, there are extended defects in the form of stacking faults and twins and things like that. Overall, this is still the unknown direction, but you do get this other kinds of stacking defects in these materials. Fine? Yes,
Yeah.
Siraj. Yes.
So why going back?
There is no reason for it. I think it is basically, say, I didn't talk about that. The 3 nanowires, the alloy nanowires that we chose, right, are basically, if you look from the bulk phase diagram, gold platinum is a phase separating system, gold palladium is a mixing system, and gold copper is an ordering system. 3 different heats of mixing, if you will, right? That's why we chose those things. Also easier to do, okay? But the point is that natural tendency is to mix, okay? Therefore, when we heat it, diffusion will happen and you will mix. Unless there's a strong thing that actually keeps to the surface, like carbon monoxide. if you heat it in inert conditions, the tendency is to basically mix.
But
They mix in all ratios, exactly.
but the fact that palladium is getting driven out,
Yes.
doesn't it somehow indicate a very high concentration of point defects, vacancies in this particular case? I mean, you are talking about temperatures which are as low as 120 degrees Celsius and 200 degrees Celsius. Doesn't that indicate, or are you using other arguments for palladium's diffusion?
Okay, so I still think the vacancy concentration is very low, but if you think about it, it's only 5 atoms thick. You just need simple atom exchanges from one layer to another. It's basically gone to the surface.
The temperature is very low.
Temperature also is, yeah, that's true, right. So I think the vacancy concentration is quite low.
Is it not like a copper nickel, low temperature, with a miscibility gap?
In gold palladium, there are some studies to show that there is some miscibility gap and things like that, but here it's pure, okay, the converse, even things that do not mix under bulk, in nano form they usually tend to mix. So there's this other part also that happens, but clearly here this is we are driving it out because of the favorable interaction between carbon monoxide and palladium.
Okay, I think I will close here. It was a pleasure listening to Ravi.
Thank you very
and
much.
wonderful talk. Please join me in thanking
Thank you.
Professor. On behalf of the director, I would like to present this to Ravi. Please.
Thank you.
We recently started some books and books.
Thank you. Thank you very much.